Hello and welcome to the first video of section 2.6 on implicit functions. At this point in the semester, we are becoming very good at taking derivatives of functions written in the form y equals f of x. But not all functions can be written in such an explicit manner. In fact, not all functions can be written. The only requirement on a function is that every x value is associated to at most one y value. Take for example the equation y equals the square root of 9 minus x squared. This equation graphs the top semicircle of a circle. But how do we know this? Well, squaring both sides and moving x squared to the left-hand side, we obtain the equation of a circle. Remember, this equation fails to be a function as a circle fails the vertical line test. The equation of a circle, though not a function, defines two functions, the function of the top semicircle and the function of the bottom semicircle. In fact, there are multiple functions implied by the circle equation, not just our two examples. We could take the piecewise function f, which gives the top of the circle when x is not negative and the bottom of the circle when x is negative. Or we can define a function g by taking the domain of our circle and chopping it up into pieces, and just choosing a y segment for each piece, either the top or the bottom. We now have g graphed in red. Notice that g is a function as it passes the vertical line test. When a function is written in the form y equals f of x, where the y variable only appears in the left-hand side, we say that the function f is explicitly described. The equations of the top semicircle and bottom semicircle are written explicitly. In fact, every function we've encountered before today has been explicitly defined. When a function is hidden in an equation, that is, a function of y depending upon x, which is implied by the equation, we say that the function is implicitly described. Take our equation of the circle, x squared plus y squared equals 9. We've seen four functions which have been implicitly described by this equation. Explicit, as in for a given x, the value of y is clearly understood. Implicit, as in for an x value, the y value is implied. You need to solve another equation in order to find what y is. For example, if in our circle equation we're told that x is equal to 2, the y value is then implied by the equation 2 squared plus y squared equals 9. Subtracting 4 from both sides, we find y squared equals 5. So when x is equal to 2, y is found by the equation y squared equals 5. And as we know, there's two values which will give us that. Y is equal to positive square root of 5, and y is equal to negative square root of 5. It is not clear from the equation which one is needed for our function. Not all functions that are presented implicitly can be written explicitly. How would you solve these equations for y? For our purposes, it is unnecessary to take a function implicitly described and write it explicitly. In our second video, we will extend our differentiation techniques to implicit functions. As a final example, let's look at our top equation. Our equation defines a curve, and it implies many functions. All we need to do is erase enough of the curve so the remainder passes the vertical line test. Notice the only issue happens in our loop, and if we erase enough of our loop, we now have a function. General curves still have tangent lines, which along with implicit differentiation is the topic for our second video.